Hello friends, in our last video we concluded that a line is a collection of points going endlessly in the two opposite directions. Now consider two parallel lines. You know what parallel lines are, right? Parallel lines are the lines in a plane which do not intersect at any point. Also, the distance between the two parallel lines is always the same. In this video, we will be talking about shapes between two parallel lines. The statement shapes between two parallels can be quite vague, as we can have any shape between any two parallel lines. Here are some examples of the shapes between two parallels. However, shapes between two parallels refers to something quite specific. It talks about shapes like these. So, how do we define this? Well, a shape between two parallel lines is a shape that has one of its sides on one of the parallel lines and the opposite vertex or the opposite side on the other parallel line. Now, let's take two parallel lines and draw two triangles between them. Triangle ABC and triangle DBC. What can we observe about these two triangles? The first observation is both these triangles have the same base. We can clearly see it, right? The base of both these triangles is BC. Now, the second observation is both these triangles are between the same parallel lines, as the common base of both the triangles lies on one of the parallel lines and the opposite vertex to the common base of both the triangles is on the other parallel line. Remember these two observations, as they will help us a lot. This time, consider a trapezium A, B, C and D. Now extend the line segment AB till E. Join DE and CE. By doing so, we will get the triangle DEC. So here we have two figures, trapezium ABCD and the triangle DEC. Now tell me whether these observations are true for these two figures or not. The first observation is that both of these figures must be on the same base. Yes, they are on the same base. The base of the trapezium is CD, which is also the base of the triangle DEC. Now, the second observation is that both these figures must be between the same parallel lines. Now, let's see whether this observation is true or not. In a trapezium, we know that a pair of opposite sides must be parallel. So, in the trapezium ABCD, the sides AB and CD can be seen to be parallel. Also, AE and CD will be parallel since AE is just an extension of AB. So, we can conclude that AE and CD are parallel to each other, which implies that the trapezium ABCD and the triangle DEC lie between the same parallels. Now, here are some figures and you have to find whether these two observations are true for these figures or not. You may pause your screen and do it. In the first figure, we have the parallelogram PQRS and the triangle QTR. First, let's check the first observation, which is that they must be on the same base. Now, if we rotate this figure, we can clearly see that the base of the parallelogram is QR, which is also the base of the triangle QTR, which implies that both of these figures have the same base. Now, even the second observation is true for both these figures, since PQRS is a parallelogram, which implies that PS is parallel to QR. And we can clearly see that both the parallelogram and the triangle lie between these two line segments. So, for these two figures, both the observations are true. However, if PQRS were a trapezium with PQ parallel to RS, then both the triangle and the trapezium would not be between the same parallel lines, despite having the same base. In fact, only the trapezium would be between the same parallel lines, but not the triangle. Now, for the next figure, we have two triangles, A, B, C and D, B, C. Again, the first observation, that is, both of these two figures must be on the same base, which is clearly visible. The common base of both these triangles is BC. Now, what about the second observation? We can clearly see that both of them can't be between two parallel lines. That is, if we draw a line parallel to BC passing through D, we can clearly see that triangle ABC is not between those two parallel lines. On the other hand, if we draw a line passing through A and parallel to BC, we can clearly see that the vertex D of the triangle DBC does not lie on that parallel line, which implies that triangle DBC is not between those two parallel lines. So, the second observation is not true for these triangles. In the third figure, there are two triangles ABC and DEF. These two triangles are between the same parallel lines, but they are not on the same base. So only the second observation is true for these two triangles. I know, you may be wondering why we are making a point to observe the same two things again and again. With the help of these two observations, we can deduce an important result concerning the areas of some figures. Let me show you. Let us consider two parallelograms A, B, C, D and E, F, C, D. Now we can clearly see that both these parallelograms are on the same base and between the same parallels. Since these two observations are true for these two parallelograms, we can conclude that the areas of both these parallelograms are equal. That is, area of the parallelogram ABCD is equal to the area of the parallelogram EFCD. I know, you must be thinking why it is so. Let's prove it. So we are going to prove that if two parallelograms are on the same base and between the same parallel lines, then the areas of those two parallelograms are equal. It's quite intuitive, right? We don't need any formula for this. Let's start by writing what we want. We want the areas of the parallelograms ABCD and EFCD. The area of the parallelogram ABCD can be written as area of the triangle DAE plus area of DEBC. Now, the area of the parallelogram can be written as area of DEBC plus area of the triangle CBF. Since both the parallelograms have DEBC in common, we can ignore it. Now, essentially, we have to prove that area of the triangle DAE is equal to the area of the triangle CBF. If we prove that, then the area of the parallelogram ABCD will be equal to the area of the parallelogram EFCD. But how can we prove that the areas of the triangles ADE and CBF are equal? If you remember, in our last video, we concluded that if two geometric figures are congruent, then their areas are equal. So, if we can prove that triangle ADE is congruent to triangle CBF, then we can conclude that both their areas will be equal and our problem will be solved. So, our aim is to prove that the triangle ADE is congruent to the triangle CBF. For this, consider the two parallelograms ABCD and EFCD. In the parallelogram ABCD, AD is equal to BC and AB is equal to CD. Since we know that opposite sides of a parallelogram are equal. Now, in the parallelogram EFCD, we can conclude that EF is equal to CD and ED is equal to FC, since the opposite sides of a parallelogram must be equal. Now, let's observe these observations carefully. Here we can see that AB is equal to DC and also EF is equal to DC. So, we can conclude that AB is also equal to EF. So, AB equal to EF. Now, in this figure, if you observe carefully, AF is a straight line and both AB and EF have a common part, which is EB. Now, if we subtract EB from both the sides of this equation, we get AB minus EB equal to EF minus EB. AB minus EB is nothing but AE and EF minus EB is nothing but BF. So, we proved that AE is equal to BF. Now consider the triangles ADE and BCF. We proved that the corresponding sides of both these triangles are equal, which implies that by SSS criterion, both these triangles are congruent, which implies that the areas of the triangles ADE and BCF are equal. Now, the area of the parallelogram ABCD is the sum of the areas of DAE and DCBE. We just proved that area of DAE is equal to area of BCF since both those triangles are congruent. So, we can replace the area of DAE by the area of BCF. So, the area of ABCD is equal to area of CBF plus area of DCBE. Now we know that area of CBF plus area of DCEB is nothing but area of the parallelogram EFC. So we proved that the area of the parallelogram ABCD is equal to the area of the parallelogram EFCD. From this we can conclude that parallelograms on the same base and between two same parallels are equal in area. This is a theorem and we just saw how to prove it. Remember this theorem because it will help us in solving many problems. There are many more ways of proving this theorem. You try to find some more approaches and meet me in the next video where we will discuss some problems related to this concept. As of now, let's summarize what we have learned so far. If two geometric figures are congruent, then their areas are equal. A shape between two parallels is a shape that has one of its sides on one of the parallel lines and the opposite vertex or the opposite side on the other parallel line. Parallelograms on the same base and between the same parallel lines are equal in area.